Okay, any questions before we start? Okay. So, what did we do last time? It's been a while. So, we did MSSM, right? We wrote down the general structure of the MSSM based on the gauge symmetries, and we wanted to keep the fields to the minimum, whatever is required in the standard model. We just added superparticles to that, and then since supersymmetry has to be broken, for now we explicitly broke supersymmetry, but by adding only what were called soft terms, which did not reintroduce quadratic divergence in the Higgs sector. And we saw some examples of how adding some scalar mass terms did not reintroduce the quadratic divergence. So that is the main reason why supersymmetry is got a lot of attention and is getting a lot of attention for phenomenology, because it stabilizes the Higgs sector at the electroweak scale. So we wrote down general supersymmetry breaking terms for the MSSM, or we called it the MSSM. Now today we'll see some examples of where these things arise in, what kinds of theories these things come from. Other way of looking at it is there is some more elaborate structure or UV completion that generates these soft terms, which will impose relations among the general terms that we added in the MSSM. So we'll see explicitly what kinds of relations they impose or they bring about, and we'll end up relating various parameters of the MSSM. The MSSM has some 100 plus parameters, and we will see examples of a few mediation mechanisms where supersymmetry is broken in a hidden sector and is mediated to the MSSM through some mechanism, and we'll see some examples of that, and we'll see the relations that they will impose. And when we do the more collider based, like limits and prospects and so on, we'll go back and say what does it imply for each one of these mediation mechanisms. So that's the goal for today. We'll just see some examples of UV completions which will relate the MSSM parameters. Okay, so that's the goal. So before I give you examples of that SUSY mediation mechanisms, let me tell you something about the Goldstino or the massive gravitino. So when you complete supersymmetry, we have been talking about in this course mainly on global supersymmetry or only global supersymmetry, where the supersymmetry infinitesimal parameter is a constant parameter, is a rigid symmetry transformation. But if you make the infinitesimal parameter function of space-time, then you will get local supersymmetry similar to a gauge theory, like global gauge invariance or global invariance versus gauge invariance. The same relation there is between global supersymmetry, which we have been doing, and supergravity, which we have not done. But for phenomenology, we will find that it is sometimes very important to include the gravitino, because some of the particles will decay into the gravitino, which has R parity -1, and in some cases can end up being the lightest supersymmetric particle. And towards the end, we briefly saw that the lightest supersymmetric particle is important for phenomenology, because all of the heavier particles, if they get produced, eventually will decay to the LSP. And it happens that in some cases the gravitino will become the LSP, and so we have to say something about the gravitino. So we'll only look at it as a cheat, so we have not done supergravity, so the gravitino really is the partner of the graviton, and we'll just pick aspects of it, and then enough to just be able to write down an effective Lagrangian for the gravitino, so that we can at least talk meaningfully about what happens to these decays and so on. So keep that in mind. The goal is only to pick out the aspect relevant to the decays of some heavy particle to the gravity. It's not by any means meant to be an introduction to supergravity or developing the formalism of supergravity or anything here. So I'll just highlight where this comes from, and we'll just quickly write down what the effective Lagrangian for the gravitino is. So the gravitino is massless, being the partner of the graviton, which is massless, right? The gravity is mediated by a massless field, and so its partner is also massless, but there is something called the super Higgs mechanism, which is the generalization or the supersymmetrization of the Higgs mechanism, where the gravitino will end up being massive. And we'll just see how it is. We'll just write down the connection between the massless gravitino and how it becomes massive. So that goes by the name of the super Higgs mechanism, and it becomes massive by absorbing what is called as a Goldstino. And we'll write down first the Goldstino where it arises, and then next how the gravitino absorbs this Goldstino and becomes massive. Okay, so let's start with the Goldstino. So the Goldstino is a spinner, so it's a spin 1/2 object, and it arises when supersymmetry is broken spontaneously. So whenever a symmetry is broken spontaneously, global symmetry is broken spontaneously, there is a massless field. There is a Goldstone. In the case of the standard model, we call it the Goldstone boson because it's a boson. But in the case of supersymmetry, because the generator is a spinner, the massless mode is a spinner. So it's a Weyl spinner, so we just call it G twiddle. And so this is a spinner because the generator that gets broken is a spinner. So now to explicitly, let's take an example of spontaneous SUSY breaking, and identify the massless mode. And we'll just take some example theory which has spontaneous supersymmetry breaking, and we'll just explicitly identify the Goldstino. We'll just see the origin of why it is a massless field and how it arises and so on. So let's take a U1 theory with gauge theory with and a chiral multiplet, some number of chiral multiplet phi I. Right, so vector multiplet has a gauge field, the gaugino and the D term, and the chiral multiplet has a scalar, fermion, and the F term. So we'll just take this theory, and let's say the superpotential is W of these chiral fields. right? Now we have seen, using this, how to construct a supersymmetry invariant theory. So I'll not bore you with all the details. You know how to do it. I'll just write down the Lagrangian terms that are relevant, the mass terms that I need. So let's just look at the spinor mass terms. So there's minus 1/2. So this notation is okay, right? I don't know. This is, I'm writing in metric space, so this just is a constant factor minus 1/2, which I've pulled out. So you can just check that this is what comes out for the fermion mass terms. And again, Wij means two derivatives with respect to the phi I and phi j, right? Thought of as just scalar fields. So you just differentiate with respect to the fields phi I and phi j, this superpotential. And that is what the psi I psi j bilinear will be. So this is just picking out the f term, or rather the theta squared term, right, of the W. So let's just identify this or define this mass matrix as MF, and we just notice that if we define this object, let's say that there is some D term breaking and F term breaking with these vacuum expectation values. So just consider this linear combination of lambda. So it just means that d over square root of 2 times lambda plus fj times psi j. So you just take this object and we see that mf times g twiddle is 0. This is something which this relation is true, and you can see because d, so we'll just take the first row, this times that, so we'll say square root of 2 g, because there are two things. If I do this, so this is one, qj star, and then fj. This object is 0. This is just a restatement of the gauge invariance of the superpotential. So if you just, so I have to tell you that fj, this is on shell. So fj star that is true on shell. So this is just the constraint equation for f. And if you just plug this in, you can convince yourself that this is what is required in order for the superpotential to be gauge invariant. This is just a restatement of that. Sorry.
What is it? MF is only WIG or the full matrix?
Oh, sorry, the whole matrix. The fermionic mass matrix. So if I call the fermionic mass matrix MF, then this is true. This is a matrix equation. No, this is an observation, and I'm justifying why it is that. This is all a cheat, right? Somebody cleverly noticed all this and we just stated now that. I'm sure people work through in many different ways in order to realize these things, but now we just make the observation that these are true. And I'm justifying this. So this has two things, so I can take first row times this thing, right? That will be one thing, and this then second row times that one. And I'm trying to tell here why does that both rows multiplied by that thing is 0. So the first row times this will just give me this times that, right? Because this is 0. And this is true because of just the gauge invariance of the superpotential. And the second, this times this. So that will be square root of 2 GQI phi I square times D or square root of 2 plus Wij Fj. And this is 0. You can show by just due to the minimum. So I'll skip the details. It's quite trivial to show this, to show 2. So this is clear, right? So I just took the second one times this thing, and the claim is that that is 0. And to show this one, you just write the potential. So let me just write this as that, and as V is half T squared. I'll omit the phi A Leopoldus term. You can do it with that, but here I'll just omit it. So if you just do the construction for the supersymmetry invariant theory, the potential part is just given by that. This you have seen many times, right? I don't have to do more details on that. So we just look at the minimum condition. So the dV dFL 0 dV dd equals 0. So these will give me all the constrained equations for F and D. And I substitute back in. So I'll skip all of the algebra. I've done this once already, so there's nothing very illuminating about all this. So and then of course dV d phi L. So you impose these conditions that this be at a minimum. And then we'll just find that all of these three just imply this is just this condition. It just follows from the equation of motion. I just do that for phi L. You can just check this later if you want, but it's pretty trivial. So these two are then true, which just means that this equation is true. So again, this is written in this lambda psi I basis. This just means this Goldstino, this G twiddle is D over square root of times square root of 2 times lambda, and then Fj times psi j. So that linear combination has this property. So therefore, if I rotate the basis to now have one of these as the mode, let's say G twiddle, and this just says that G twiddle will be massless. and that is the massless mode, which we have found after diagonalizing this. You can, instead of this, you can just diagonalize this thing and get this also. It's the same thing. So this is just a quick way to identify that G-twiddle is massless. Okay, so notice G-twiddle is some non-trivial object F. Right, or let's say some f j is non-zero or d is non-zero. Because if both of them don't get a vacuum expectation values, this is not saying anything, right? So it is saying that in the presence of some spontaneous supersymmetry breaking, you can identify the Goldstino. So if only f is 0, then you just forget about this thing. So this is just some linear combination of the psi j's, right, which is the Goldstino. On the other hand, if only d is non-zero and f is 0, then the Goldstino is just this lambda, this gaugino. And you can generalize this to many gauge groups and so on. So this is just with one gauge group with one vector multiplet, but I can have a product gauge group and it will be linear combination of those gauginos and so on.
Can we just break D? Are there models where only D gets back?
So it is hard. So I think, I don't know if there are examples. So within the standard model, I don't think there are any. The problem is if you try to do that, you will end up giving webs to some of the scalar fields, and that will end up breaking color or electromagnetism or SU2 in an uncontrolled way. So it is hard. So people normally introduce a different, there are examples of introducing an extra U1 and then breaking using the, that certainly is there. But within the standard model, I don't think there are any actual working models of Deton breaking. Yeah, if you can write down some model where the D gets a non-zero vacuum expectation value, where while leaving all of the colored and electromagnetically charged ones without webs, then it's good. You can try it out and see if you can do it. So this just goes by the name Goldstino. And all of this is just an example of the fact that spontaneously broken supersymmetry leads to a massless mode. This is explicit demonstration of that in this simple model. It's quite generic, but because I have not specified what the exact form of the superpotential is, so in that sense it is generic. And this is how it will work in most models. So let's now look at the relationship between this Goldstino and what happens to it when I go to supergravity. So this is the gravitino. So you can, I just take some relations from Martin's review here. Even he does not do supergravity fully. If you really want the construction of supergravity, you should look at Wessenberger or one of the supergravity reviews. But he gives enough, again, to just motivate what is going on here and to identify the effective Lagrangian. So let's just take the pieces that are relevant to the gravitino. So the gravitino is a spin 3/2 object. right? So the graviton is spin 2 and its super partner is spin 3/2. And from so from the Noether prescription, you can identify when you have a symmetry of the Lagrangian, you can obtain the Noether current. And if you do that for the supersymmetry transformation, you will find the Noether current. So this is a claim that from the supersymmetry, the symmetry, you can obtain the Noether current which looks like that. I've certainly not derived this, but perhaps you can get this one. I just took it out of Martin's review. And if some f, let's say we just restrict to f breaking. We'll not do any de-breaking here, so it's just if some f term gets a vacuum expectation value, we know that this symmetry is broken spontaneously, and the current conservation, so this is true, right? It's just current conservation. But in the presence of this f breaking, let's just isolate some pieces of this. How does this current conservation look like? So you isolate pieces which have this non-zero f term. And everything else you call as J mu alpha, and there are other things which don't include this thing. So let me just say this J mu alpha is sigma nu, sigma bar mu, psi I alpha. So you need the form of this in order to get the coupling of the gravitino to matter. So you just take pieces of this and define some of them in J mu alpha and only isolate the piece that depends on this non-zero f term of this chiral superfield which got a web. So because it is only f breaking, so the G twiddle is now only going to include some linear combination of all of the f's. And G twiddle is with for, I'll just write it like this. It depends on the exact model whether this is realized or not, so I'm just looking at the case where only f is gets a non-zero vacuum expectation value. So you take this one, so let's just say this. Take this as just the equation of motion for this d-twiddle and write so now we know what equation g-twiddle has to satisfy, and so you just write down an effective Lagrangian for this g-twiddle. And so that L effective So if we just take the equation of motion of the g-twiddle, you will get back this this equation. It's just renormalized. The 1 over f has been renormalized to put it in the interaction and to get a canonically normalized kinetic term. But if you just take this and get the equation of motion for g-twiddle, you will just get back the equation that we had. So therefore, that can be thought of as an effective Lagrangian for the g-twiddle. So now this implies so remember, this is not a full derivation of anything. It is just like trying to pick out pieces that we need for phenomenology. We just want to see how the Goldstino couples, because that will end up dominating the phenomenology in some cases. So we cannot certainly afford to omit it completely. This implies so our main goal was to extract these interactions that this Goldstino has. Lambda, and this is A mu. So this follows from just the form of this thing. So there is a psi, phi, and Goldstino coming from here, right? It has some 1 over f. Each interaction is proportional to 1 over f, and then you have the g-twiddle from here, and then the psi phi here, or the lambda and A mu. So that just gives me these two interactions. So from this effective Lagrangian, you can get these interactions, which is all we need for figuring out how the Goldstino in this case decays. So why did we bother with the Goldstino interaction? So in supergravity, due to the super Higgs mechanism, one can show that this G twiddle is the so the massless gravitino has only two polarizations, whereas a massive spin 3/2 object has four polarizations. And the extra 2 degrees of freedom comes from the G twiddle for a massive. It's the same way that Higgs mechanism works. In the standard model, the massless gauge field has 2 polarizations, and a massive one has 3 polarizations, so extra polarization comes from the Higgs, right, from the Goldstone. And the same thing is here, so this has 2 polarizations, massless, and a massive one has 4, and the extra 2 comes from the Goldstone fermion in this case. And so if you look at processes, you can show that when the F is not too large, if, let me write it as F is much lesser than M Planck. So due to this interaction being only suppressed by 1 over F, whereas all gravity effects you would think is suppressed by 1 over M Planck, right? So all the gravity things we can safely ignore at low energy because it is suppressed by 1 over M Planck. But the reason we could not ignore this object is because we find that this interaction does not go like 1 over M Planck, but goes like 1 over F. And so if 1 over square root of F is big, so if F is, or square root of F is much lesser than M Planck, then this interaction can become relevant. It's no longer 1 over M Planck suppressed, right? And therefore we had to say something about it because it can become important. You cannot dismiss it as saying that it is 1 over M Planck suppressed and therefore irrelevant for phenomenology. We do find that because of this Goldstino component, it's really the super Higgs mechanism, the gravitino phenomenology starts becoming important through its Goldstino component. And so you can just work it out in this thing. So whenever you have some process involving the gravitino, it is sufficient to just include its Goldstino component and compute all decay bits using its Goldstino component and so on. Because the other 2 polarizations are really suppressed by 1 over M Planck and will not be relevant. So only the Goldstino degrees of polarization will get produced. So for later we can just work out, let's say that some heavier particle, let's say the Goldstino is lighter in this case, or the gravitino is lighter, and if we work out some heavy particle, some supersymmetric particle, goes to some number of standard model particles and a Goldstino. Using these, everything is worked out. I told you what the interaction is, and these are the vertices. So you can just work out the decay width of this supersymmetric particle decaying to the gravitino, and as I argued, it is sufficient to just look at the Goldstino component for this thing. explicitly we see this 1 over f come here. So this will be the decay width. So once we know this, we can go ahead and do all of the phenomenology, the collider signals, all of that for a gravitino. So we'll explicitly see when we do gauge mediation, where in gauge mediation the f is not, where this is true, the f is not too big, or square root of f is much lesser than m Planck. We will face this issue that the LSP will be the gravitino and will become relevant. So every single supersymmetric particle in the case of R-parity conservation, if it is produced at the LHC, will eventually decay to the gravitino because that is the LSP. And the decay width will be given by that formula. Any questions about this? It's a bit sketchy, but hopefully the idea is clear that if you were to do it in full, this is how you would identify the things.
When we talk about large number of gravities,
Sorry? What about?
also people say that anything
Yeah.
we have large number of gravities also models are good.
I would not say large, by you say large number, you mean number density, is that? Yeah. Yeah, overcloser. Yeah, there are various bounds, so I have not looked up of late what the bounds are. So there are very stringent constraints because it all depends on what the mass of the gravitino is and the f. So the constraints will come because of these two. So you have to make sure that it does not overclose the universe, right? It should not be so weakly interacting that if you produce the gravitinos, then you cannot get rid of them. So if depending on how the inflaton decays, if it decays to the gravitino, but the gravitino interacts very weakly, suppose I make f very large, then too much of that will be left around and will overclose. So that certainly will not be an allowed parameter space of that theory. So this overclosure will put constraints on this parameter space of mass and coupling. So if you are in the right region, there are right regions for the gravitino where you can make it work. So there are allowed windows in the gravitino mass and the couplings, which will be fine. But there are large regions which are ruled out or will not be allowed by relic density. More than that, I cannot say anything, so you'll have to look up some review. There's huge reviews written on what part of the parameter space is allowed. But yeah, you're right. So there will be some non-trivial constraint on this coupling and mass. So roughly speaking, or not roughly speaking, you can write down the relation that the gravitino mass m3 halves is just given by this f over m Planck. There is some square root of 3 factor or something. So it will relate the mass to the coupling, and so this will impose a non-trivial constraint from cosmology. So you cannot pick an arbitrary gravitino mass. Usually the way it works is if you make sure that the NLSP works properly, right, and you don't overproduce in the early universe too many gravitinos, that you have to certainly check that whatever produced all of the reheating did not produce too many gravitinos. If that is true, and then you arrange such that the NLSP gives you the correct relic density, and if it is late time decay, then eventually that NLSP will decay over long lifetime to the gravitino. And because you made sure that the NLSP relic density is what is required, then the gravitino may also come out as what is required. So that is how a lot of these models work. So the otherwise, you know, that if you take the coupling itself of that, it can give you a very long lifetime. So in fact, the lifetimes can be such that for some of these Fs, that if you produce a gravitino, it can in fact exit the LHC detector. You know, like lifetimes can be very long for the gravitino decay if F is very big. So certainly, if you make F M Planck, right, then it is a very, very long lifetime. That we can see, but it is in the intermediate thing. There's a possibility of the gravitino decaying promptly to the case when the gravitino just exits the detector. So one has to cover this entire region of parameter space. Both possibilities are possible, so people do searches including both possibilities. And same thing with relic density also. So you have to include the possibility of different Fs and then make sure that that in the model that you are looking at, that you don't overclose due to this gravitino. Okay, so let's look at one example of gravity mediation. So how do you mediate supersymmetry from some hidden sector or some sector which does not carry standard model charges to the MSSM? And we'll look at a few examples. So let me start with gravity mediation. To do gravity mediation, again, gravity mediation works in the context of supergravity. And again, we'll do the same cheat. We'll only look at things that are relevant to saying things about gravity mediation. And then we'll write down how gravity mediation works, what is the basic idea. So let me look at certain aspects. So we have been working so far, at least I suppose when Ramesh developed the formalism, it has been in the context of renormalizable supersymmetric theories, right? But supergravity is not a renormalizable theory. So there are operators that come in which are non-renormalizable operators. So let's first say quickly how it is that you can generalize the construction that we had to the case of non-renormalizable operators. So we'll write down a slightly more generic form, but very all of the basic ingredients are already there in the formalism. We'll just extend it to include the possibility of non-renormalizable terms. So for again, you can look at Martin's review for details of this. For a discussion of supergravity theory structure, let's so we'll include some non-renormalizable operators and write down Lagrangian. So I'll just write down these things. So the structure will become probably obvious to you based on the construction that has already been done. It's just putting it in a more general form. Which are the structures that arise in supergravity? So now this means that you take the d term of this, the theta squared, theta bar squared term of this object. Now phi I are the chiral superfields in the theory, and this again, this bracketed thing means take the f term, take the theta squared term, and again take the theta squared term of this thing. So this is the exact same construction that was there in the global supersymmetric case, or with the renormalizable operators, but now we generalize it to include, now there you just had this phi. What does phi twiddle mean? It just defined as star k and this thing, the hatted thing, the V hat here, is just with the gauge coupling absorbed. So this is the same thing in the case of the renormalizable thing that we wrote down earlier. We took a simple form. We just wrote it as phi I, phi twiddle star. This k was just trivial in the case that was done earlier, which Ramesh wrote down. So you just took the d term of this phi star with this gauge field included for a local gauge theory, super gauge theory, right? So it was just the d term, but now we write it in a more slightly general form, where now k can be any function of these fields, and k is called so it's called a Kähler potential. So you can take a general function of these fields, and the minimal case the renormalizable case was just k was just this term, but we can extend it by non-renormalizable terms, which we'll see some example of how we extend in some specific ways when we do gravity mediation. But right now I'll just leave it as a general thing. So this is k, and then the f. This f, this is where the gauge multiplied kinetic terms come from, right? So you just take this gauge kinetic function, which is written in terms of the d bar d of something, right? And then you take the f component of that, and we did not have this thing. It was just trivial last time it was written, but now you can take a general function of these chiral superfields, and this is known as a gauge kinetic function. Is some so remember, we want to take the f term, right? And so we want something which is holomorphic in the fields, and only if it is holomorphic will it transform as a total derivative, and we can include it in the Lagrangian. So we want this whole thing to be a product of chiral superfields. And if that is so, then FAB also has to be a holomorphic function of the fields. And then it is an allowed candidate thing. Some holomorphic function of the phi, and the minimal case was just delta AB. And we'll see again how we extend it beyond this minimal case when we do gravity mediation. But I'm just writing down the structures where you can generalize in some specific ways. And again, W is just the superpotential as before. Which is again a holomorphic function of all of these chiral superfields phi. Yes, you can. Yeah, everything that we did so far was renormalizable level. So now we write down non-renormalizable operators suppressed by some cutoff scale, which in gravity mediation will be the Planck scale. Yes, there will be, but we'll see how, if you hold your question for just a couple of more minutes, you will explicitly see why it is still relevant. Okay, so now let's start talking about gravity mediation. So let there be some, or consider some X superfield which is a MSSM singlet. So it does not have any standard model quantum numbers or MSSM quantum numbers. So consider such an X but which gets, suppose I don't need a but, which gets a wave, or I'll just say whose F term gets a wave. So this breaks supersymmetry. So supersymmetry is broken in some hidden sector, and by a field, a superfield, which is a gauge singlet. So let's write down some non-renormalizable superpotential. So it has the usual MSSM superpotential that we wrote last time, and to that let's extend it by I'm just using the notation that Martin has in his review, so you can look at that for all the details. So you can write terms suppressed by higher powers of 1 over m Planck, but we will not write it. So it will be sufficient to just stop there. And so this is just a coupling of X to the MSSM fields. So these symbolically will denote the MSSM matter fields, chiral multiplets, and then X is this new superfield whose F term gets away, breaking supersymmetry. So, and then it is coupled through these higher dimensional operators. So, this is a higher dimensional operator because at the renormalizable level, W should include only up to cubic, but now I am writing quartic, so it will be a higher dimensional operator. Which other term? This one? Yeah, this is a cubic. That's a renormalizable operator. Yeah. Ah, good point. So why is it suppressed? Oh, I guess yeah, I suppose that is just a construction that you think of mu as a dimensionful parameter, which arises from supergravity. That there could be this kind of a term that comes with a dimensionful parameter mu, and then is suppressed by M Planck.
Then you can write one more term, xx5.
Yeah, you can generalize this thing, but this is a canonical construction that people write down. Xx5 will not come about because it will not be a MSSM singlet. You need at least two fields here in order to make them MSSM singlet, right?
xx55 is double x and
Yeah, XX55 might be allowed, which will just be a renormalization of this thing. So, yeah, you can write XX55 suppressed by M Planck, which will just be a renormalization of mu, I would argue. Yeah, you can generalize this thing and try to see if there are some new features, but yeah, you have to bring about some new features, otherwise you just stick to this.
I mean, this has been phenomenally written, or you can write a supergravity Lagrangian and derive this.
It has been phenomenologically written and also argued from the supergravity that it can generate these kinds of things. This is really written in a supergravity setting, that you have some field with this X candidate field, which will in the end, this is just, I guess, taking out whatever is the relevant part for phenomenology in this bigger structure called supergravity. And you just zero in on the parts which are relevant to this supersymmetry breaking.
Probably we don't have freedom to modify the supergravity.
No, probably you do. I mean, I don't know how like restrictive this is in the context of supergravity. That's simply that I don't know. You might be able to generalize this more, but still being within the context of supergravity. Yeah, you don't make changes that you are suggesting which will only modify the things a bit and will not lead to any new thing, right? But if there is a possibility that you modify it in a way that will change the phenomenology, then it's fair game. So this minimal killer potential that we had, this thing we extended again with higher dimensional operators. And then you can keep going. So you just extended by these things. So these are all free parameters that you just are free to choose at will in this effective theory. But in supergravity, you might have some definite predictions for what those are. Sorry. Yeah.
Y, X, I, J, K. So this X and X summed over and for each X there is a Y.
No, I'm imagining only one X. one single x. You can generalize it perhaps to many different x's, but here there is only one x. So this is just some coupling. If I pick I, j, k and I stick in an x here, this is some number, right? I, j, k will sum over all of the MSSM fields. Yeah.
You assigned y to a extent x also, and you actually thought that.
Sorry, say that again.
So ijk is summed over with these indexes with
Yeah.
ijk.
Yeah.
And the x.
This is just the yx, and ijk is the index.
That's why I thought that for each x there is this y.
Yeah, you can do that, but right now I have only one x. It's just a symbol. If you want to put the x here, it is completely fine. It's some ix, huh? Yeah. Yeah, or call it you know, like call it gamma, if you will, right? It's just ijk is summed over the MSSM fields, and this is just some number. That's it. I forgot now what I had. Yx. So this is this gauge kinetic function, where you again extend it to include 1 over mp terms. And no, I mean, this is just inspired by supergravity to show that actually it is supergravity or local supergravity invariant. You have to develop more formalism. This is just a low energy effective theory coming from supergravity. You only look at whatever is a relevant thing involving some superfield that you identified as x, which gets this wave. So within supergravity setting, you have to actually work harder to show that these structures come, and in fact there is this kind of an x, and it does get a wave this way. You know, that is a harder problem, right? So right now we are just writing a low energy effective theory and imagining that there are all these suppressed terms. There is no supergravity here. It's just a low energy effective theory with global supersymmetry, but just augmented by a higher dimension operator. If you will, you can completely leave out the word supergravity and just write this down as a model, and that is what we are doing. Just writing, thinking of it as supergravity by writing M Planck, but you just write down this theory, some cutoff scale with some gauge singlet x, and then write down this theory. It's completely, that's what we are doing. So for what is relevant, so you can just forget about the scalar component and the fermionic component, and just think of it as just focus on the theta squared component, which has this f. So you can just set x is theta squared f, and then I've written down all of the functions that I need, and I've told you what x is, and then we just pick the d term and the f term of these things and write down the Lagrangian, right? So that is the Lagrangian that follows from globally supersymmetric invariant construction, which is given here, and the generalization is written down here on what those W, K and FAB mean. And this WMSSM we saw in this general notation is just written as So you can map it to the superpotential that we had written down last time. So not all of these terms will be allowed, so depending on the gauge charges of which fields you pick, some of them will be allowed and so on. Not arbitrary combination of all the 5s is allowed. So you'll have to pay attention to the MSSM gauge symmetry. And then some of these Yijk's will be non-zero depending on whether it's allowed or not. Okay, so again, if you pick out all of those D and F terms, we will get some terms which are already contained in what we wrote last time, the MSSM Lagrangian, right? It will have the same structure, and it has been constructed in a way that it will give me the same things because we wrote the MSSM in a completely general way. So whatever we get here we should be able to map onto that Lagrangian there because that was the most general structure you could have. So here this will give me specific predictions for what those things are. So first the gaugino masses that I had last time. Will just be related to this Fa here. So that will be the gaugino masses. So remember, in last time what we had soft breaking terms which were Ma lambda lambda for the gauginos, right? Lambda A for depending on the A is just the adjoint index. So if I take SU3, A goes from 1 to 8. If I take SU2, A goes from 1 to 3. If it is U1, A is just 1, right? It's just one index. So it's that adjoint index. And that gaugino masses are given by this thing. So if you look at what we had last time, you can map from here to there. So then the A terms, so remember the A terms are cubic terms in the scalars. These are again soft breaking terms. And so those A terms now will be given by So again, I'm exactly using the notation of Martin. So again, the B terms are bilinear terms. In the SUSY breaking thing we wrote down, it had H up, H down, right, for the scalars. There's too many indices here. So the M squared were now scalar masses, soft masses, like for quarks, leptons, all of those. So these are the things that come out. So depending on what these constants we stick in here, we'll have predictions for the soft masses in the MSSM. So this you see will relate things that were completely arbitrary in the MSSM soft breaking terms.
So all the soft terms that we wrote in MS, you're not writing this, you're writing only these.
No, we are writing this will give you all of those soft masses is the point.
Yeah, but we added them arbitrarily with arbitrary. That we are not doing.
No.
No, all
So
the soft terms are written here. There is no.
this is a theory for the soft terms, if you will. So you can write down a general theory which with arbitrary soft masses, or there can be a UV completion or some grander structure which will give you predictions for those soft terms. And these are the predictions for those soft terms. They are given in terms of fewer parameters, and there are a lot of parameters here. Perhaps I guess it is still true that there are fewer parameters. So you will find a lot of relations between the soft terms which otherwise could have been arbitrary. The thing that we wrote down there was completely general, and this is giving you some relations among those parameters. And in fact, you see that I, J, K now are taking chiral superfields, and you can think of them as generations. So in this MSSM, you have 3 generations, so you can pick fields from any generation. And it is easy to see that this does not tell you any constraint on how the generational thing has to be, because gauge invariance works the same way for the 3 generations, and I can take at will any, I can substitute I, J, K, any one of them. If something is allowed by the gauge symmetry, I can trivially change the generation index and it will still be a gauge singlet. And so it does not give me any relation or any understanding of the generation structure, and therefore this just means that whatever this gave us will lead to very big flavor changing neutral currents, because when there is a sector which is beyond the standard model, which has arbitrary generational structure, I can use that to mediate FCNC, and in general there will be huge contributions to FCNC, and this generically is called as a flavor problem. So this gravity mediation generically, unless we do something more and give it some structure, it will lead to flavor changing neutral currents, and that is called as a flavor problem. So this whole thing is also called as M-Sugra for whatever follows from minimal supergravity, or it's called CMSSM also, which is called as a constrained MSSM. So constrained in a special way which is following from supergravity. That's kind of the thing. So yeah. No, they are the same. As far as I know, they are the same. There might be some small differences between but for practical purposes, they are the same. Yeah, it is to do perhaps with the boundary conditions, whether you impose it at the gut scale or the gravity scale. So here, technically, you are supposed to impose all of these relations come about, or these terms come about at the gravity scale, because that's where gravitational effects are decoupling and is generating all of these non-renormalizable operators. So although you are strictly supposed to put these boundary conditions at M Planck, I don't know, for convenience or what, people just put it at gut scale, because we don't know really, at least we have some theories and some ideas about how we have to write down gut theories, and we can do the RGs and everything up to the gut scale, but beyond the gut scale we don't know what physics is operating. We don't even have good proposals for it, and so you don't know what field content is there, and you don't know how to run the RGs beyond the gut scale. And for that reason, people put the boundary condition at the gut scale. And I think the terms are related to whether you put the boundary conditions at M Planck or at gut scale. Perhaps the CMSSM means that you put the boundary conditions at the gut scale, and you do that in M-SUGRA also, so perhaps the distinction is not very big. But yeah, I'm not really sure why the two names. We can check on this. And so all of these things can have arbitrary flavor structure, and that certainly is not allowed. So if you just, we'll look at examples next time, where if you take a particular M squared, there will be very strong constraints on its generational structure from FCNC. And certainly making it arbitrary is a very bad idea. It should have some relation to the standard model Yukawa couplings. Otherwise, you are completely ruled out by flavor. In M squared and also in the A terms, anything. And FCNC means flavor changing neutral currents, like things like BB bar oscillation, KK bar oscillations, things like that will end up being too big. So remember from what we said in the first part, there is also the gravitino, which is not written here. We did not bother writing it in the MSSM, but as I said, in some cases it can become relevant. So M 3/2 is just given by F over M Planck. So to get this flavor problem under control, what people do is make so you just make the hypothesis that all of the Fa is given by a single F and all of the Kij is given by a single K. Same thing for all of this. You just so this is just relating between these things and the MSSM. The Yijk last time we wrote down, probably I wrote it as lambda, but so this was just the Yukawa couplings in the MSSM, right? So the cubic terms. So you just make the ad hoc assumption that whatever these things are will be related to whatever is in MSSM. So same thing with the mu, so it should be related to the mu ij which was in the MSSM. So these things there is no good understanding from supergravity as to why these should come about, but you just make the assumption based on phenomenology, because this will give you control over FCNC if you do this. And so just make the assumption which is completely ad hoc from the point of view of supergravity. There is no understanding why supergravity should lead to anything like that. And moreover, you assume all of these real. So these are to keep things like EDM under control. So if you put two big phases, then the electric dipole moment of the electron and the neutron and all of these things come, electron basically, or the muon will come out too big. So with these assumptions, so we have made many different assumptions here, and which means that it will reduce the number of parameters further from what we had. So now all of the gaugino masses, the 3 to 1, I mean just at the boundary condition, at the gravity scale, will be just given by, or at the Guts scale. You can think of it as a Guts scale for the reason that I mentioned. So you can just, this will just imply that all of the gaugino masses are given by one single mass parameter at the high scale. And these are all the quark masses. So for all of them, Q, U, D, L, E. So all of them are just given by m0 squared, one mass parameter, and that it will be flavor diagonal, which is crucial. So if you have flavor diagonal, then there are no flavor changing neutral currents. So if you have flavor off diagonal terms here, that is what leads to FCNC. So this assumption, you can see, will just lead to a flavor diagonal m0 squared, and one common mass scale for all of these scalars. So it's a drastic reduction in the number of parameters, as you can see. And the soft masses for the H up and H down will be equal and given by the same m0 squared. So all the atoms again are given by the same scale for the U, D, E. Well, let me write it as U, D, E, given by the same A0 times the Yukawa coupling, the corresponding Yukawa coupling. And again, this is good from the point of view of FCNCs. This is called alignment. So if you align it with the standard model quark or lepton Yukawa couplings, then you will also have flavor changing neutral currents under control. When I do flavor, I'll try to point these things out a little bit more. So again, the B mu term is related to mu. This is what this is saying. And you can write down what these things are in terms of these quantities, F's. So m1/2 is F in Planck, m0 squared, F over m Planck. Oh, sorry, K plus n squared. And the A0 plus 3n F4 m Planck. Then the B0 . Yeah, all of this is there in Martin's review, so I'm reproducing that thing. So now we just write down what these things are in terms of these simplified number of parameters. And so here you see that ultimately we want to make them, these objects, at least as heavy as about a few hundred GeV, because no experiment has seen that so far. And depending on which probe that you look at, it will impose various constraints of the order of a TeV or so. If you look at flavor changing neutral currents, it will still impose some constraints even on this one, because there are new particles that can mediate FCNCs, and it will put all of these constraints roughly of order of a TeV. So it can be 100 GeV if it is some particular generation thing or so on, but I'll say roughly a TeV. And so we need, if we need all of these to be roughly a TeV for making things safe from constraints, need the MA or the scalar masses roughly of the order of a TeV, right? There is no simple answer to that. As I told you, like depending on which particle it is, if you ask what is the limit on, huh? No, that does not make any sense. It depends on what assumptions you make for the spectrum, for the theory. The model will be very dependent on these assumptions. What are the particle spectrum, what hierarchy it has, which one is heavier than which one. All of these matter in saying what is the limit. You cannot give one limit and say, okay, this is the limit on a stop. You cannot say that. You can only say the limit on the stop if the neutral is this, is that, if the things like that. And so it will all be dependent. So you cannot give one single number. And I'm just saying roughly it will come out to be of the order of a TeV. Like in some cases it can be 100 GeV if you take the limit on a Beano or something. It will be much lower than if you take for something like first generation Squark, things like that. First generation Squark must be beyond a TeV. Already we know that from EDM and so on. Whereas limit on a stop may not be so tight. It can be few hundred, 300, 400 GeV and so on. And something on a neutral can be much lighter, 150 or something may be allowed, and even lower in some cases. It depends on the exact model that you are working with. So I'm saying roughly for argument's sake that it is all of the order of a TeV, and if that is the case, then we see this number, again depending on what f is, but this is order of magnitude. Depending on what f is, it will change depending on the model and so on. So f over m Planck should be of the order of a TeV, which means this root f should be around 10 to the 11 GeV, right? So f has dimensions of GeV squared, right? F term has dimension 2, mass dimension 2, and this root f. So if you want f over m Planck, all of these masses to be of the order of a TeV, the SUSY breaking f that you need is 10 to the 11 GeV squared. So you can roughly think of this as SUSY breaking dynamics happening at 10 to the 11 GeV. So that's what gravity mediation needs from the relations that we have seen. Okay, I wanted to do gauge mediation, but I have run out of time, so I'll do that next time. So any questions about this gravity mediation?
So X can you take as right-handed mediation?
That's a good question. I was thinking the same. So I have not reached a full answer yet. So yeah, you can try it.
Because
I don't know if.
the order of magnitude is also same. Right?
That's right.
Seesaw type mechanism.
Yeah.
So it's
Yeah.